resolution transmission electron microscopy. I would like to quickly introduce the speakers. We'll have 3 speakers today. Hiroya Miyazaki is the CEO and the co-founder of MEL-BUILD. MEL-BUILD is a company developing and designing the unique solutions for electron microscopy characterization. Jeffrey Streger is the founder and the president of Rave Scientific. Rave Scientific is a key channel partner in providing electron microscopy capital equipment, sample preparation, and consumables to all the scientific and industrial community. And Doug Wei is application and sales engineer with Rave Scientific. Ray has an extensive experience in the field of electron microscopy technologies, TEM, SEM, FIB, and dual beams. Without further ado, I will give the stage to Jeff.
Thank you, Anna. Thank you. Well, on behalf of Rave Scientific and MEL-BUILD, I wanted to thank everybody today for giving us the opportunity to participate in the MIT Tool Talk. Very excited about that. Today, we're going to talk about the challenges of acquiring atomic scale information at cryogenic temperatures in the transmission electron microscope. So for a lot of you that have a lot of experience in TEM, you all know that high stability is essential for acquiring atomic scale information in transmission electron microscopy. And this is especially true in the case of materials that are conducive to cooling. So what we're going to talk about today is we're going to talk about some of the challenges that are associated with cooling or trying to cool and acquiring data at the atomic scale. And then we're going to introduce a new solution, I would say not new, but another opportunity or solution called the MEL-BUILD Double Tilt LN2 ATMOS Holder Defense Holder. This newly designed holder is actually double tilt, which for some of you material scientists, you'll appreciate that because most of the holders, if not all the holders that are out there that are cryogenic, are single tilt. And so for the material scientists that are out there, I think what you'll find is that having a double tilt will open up some other places that you're used to getting and acquiring crystallographic information. So here's the agenda for today. Meet the presenters, MEL-BUILD, Rave, we've done that already. We'll give you a brief overview of the 2 companies. We'll do that very quickly because this is really about technology today. We'll talk about the challenges of acquiring atomic scale information at cryogenic temperatures. We'll do a brief overview of the relevant applications, and then we'll give you an overview of the MEL-BUILD Defense Holder. And then at that point, we'll have an open forum for questions with the audience. So we talked about that. There's some pictures of us, Hiroya on the left, me in the middle, and then Doug on the right-hand side, okay? And here's a bit overview of MEL-BUILD. So founded and established in 2006, Hiroya and his father founded this company. He leads a team of very talented people in Japan. And if we look at the capital, their total gross revenue was $10 million Japanese yen. And then if we look at the history, you can see that they've been progressing, and I think that what's taken notice for a lot of TEM microscopists out there is the quality and the performance, especially of the holder that we're going to talk about today. Their vision, okay, they want to match. Their vision is to manufacture innovative TEM holders and solutions for electron microscopy. Obviously, this is made in Japan, to meet the demands of all microscopy users, to enable academia with their ideas and innovative Japanese manufacturing, and to continue and excel in this area and all the above areas. There's a picture of Roya on my left, okay, maybe, yeah, on your left, okay, and there's his members of his technical staff. Shui Ikazawa is here today also on the call, and again, this is their vision and mantra, which is to bring innovation to the world with technology from Japan. So our company, Rave Scientific, is located in the Garden State of New Jersey. We're a key channel partner, as Anna said, providing electron microscopy capital equipment and sample prep solutions and EM consumables via our our Rave Scientific e-commerce website to the scientific and industrial community. These are some of our principals that we represent, MEL-BUILD being one of them. We're also the representatives for Zeiss electron microscopy products in the Central Atlantic Territory, coating systems, vacuum products, emitters, plasma cleaners, and laser desktop solutions. Won't go too much into that, but these are the brands that we represent. This is our team, left to right, me, my wife Lisa is the manager of operations, Rod Hoy is our EM application specialist, and then Dr. Doug Way, who is our sales and application engineer, who will support the talk today. So let's talk a little bit about the challenges of acquiring atomic scale information at cryogenic temperatures. So this is just feedback that we've received from a lot of end users that have gone the route of working with materials, okay, that that you want to cool, and obviously there's issue of beam damage with battery materials, polymers, anything with light atoms. But some of the challenges is that drift tends to be problematic due to the goniometer and the cooling. And this not only presents challenges for just acquiring general images, but challenges with EDS analysis. And typically cryo holders are not set up for EDS. They're mainly designed for life science in mind, but not material science. And it tends to take a long time to get to a point where you can start acquiring data once you cool your sample down. And again, as I said, most cryo holders are single tilt, and these presents challenges with crystal orientation alignment. And then there definitely are challenges with transferring the sample to the TEM, which exposes the sample to air. And what we're going to talk about here as we get into the technology is that we have a vacuum transfer system. And I'm going to let Doug go into that in more detail. When we look at the relevant applications and areas of research conducive to cryogenic TEM analysis, obviously the big one is lithium-ion battery research, organic photovoltaic polymers and biomaterials, perovskite solar cells, quantum materials, accessing a temperature regime, studying materials where interesting things happen. Low temperature phase transformations relating to structural properties at the atomic scale. So all of this can be applied to having a holder and technology that would allow you to take the materials down to, in most cases, negative 170 C and having a stable material to acquire the EDS and the images that you need in the TEM. So with that said, I'm going to hand this over to Dr. Doug Way, and Doug is going to take us through the specifics of the holder. And what we're going to do here is kind of outline the results that we have both from a Joule arm and then also a Talos Thermo Fisher transmission electron microscope, and then go over the specifics of and design of the holder. So Doug, without further ado, please take it away.
Thank you, Jeff. So in the next slide, we'll talk about this new holder that is specifically designed for material science applications at cryogenic conditions. So this is a summary of this holder setup here. So we have a unique controller that can control temperature to the precision about plus minus 0.005 degrees Celsius, and a goniometer cover that fits this Joule arm to handle very well. That really reduces the influence from the environment. I mean, the airflow, temperature fluctuation, reduce that to a level that becomes a minimum to influence the imaging part. And a stand, which is a small tool that helps the user to load the samples to the TEM rod with great ease. Because so if you have a glove box and you have samples there, you have your TEM holder there, So to operate from outside of the glove box, to those tiny screws, tiny clips, and loading, unloading specimens is very tough. This part I've been practicing for many, many years. I know how hard it is. So this small workstation or small tool will help user to operate from outside of the glove box and to accurately, securely load the specimen to the sample, and some small little tools to, for loading specimen. So if you look at the number here, so we have a double tilt holder, which is very unique, designed for material science applications at the cryogenic conditions. As Jeff mentioned, most of cryogenic cryo holders, they are designed for life science applications. So they tend to be single tilt holder, but that is not enough for material science the research, because we need to align the crystal orientation so that we can find the zone axis of the sample. So here we have a double tilt holder, both X tilt direction and Y tilt direction can go plus minus 20 degrees, which is already very terrific. And the temperature can reach to minus 165 degrees Celsius. So this is also a very, very good range that people studying, beam sensitive materials. So once we pass something like minus 120, 110, so we are in a region that radiation damage is being greatly reduced. The transfer time, the settling time of temperature is about 1 hour. Normally, so if you have cryo TEM experience, the settling time, from room temperature to 170 degrees Celsius or in the vicinity, normally takes more than 1.5 hours or 2 hours. So here we have a holder designed to have a quicker settling time, and the drift is minimum. So if you look at the numbers, that it's not great, but if you look at the images, that really tells you, the drift is mitigated very well with this design. Jeff, can you go to next slide? Okay, so this is an example of very typical silicon dumbbell image, atomic resolution image with temperature at minus 170 degrees Celsius, a very low temperature. And we have a STEM image here to see the dumbbell here. Then, so the resolution is clearly showing on the second image. We see the atoms are clearly acquired. The image shows that the resolution on this sample. So this is this is an indication of the holder that works at this very low temperature, still retain very good drift mitigation property. Jeff, can you go next slide? So this is also a high-res STEM image of a very typical STEM sample, high-resolution STEM sample, strontium titanate. This is, we see the atoms at the atomic resolution on both the high-def image and bright field image. This image was acquired at minus 169 degrees Celsius. So this tells us, two key advantages of this holder. First of all, this holder goes to minus 170 or in the vicinity of the 170 degrees Celsius, which is about the lowest temperature most of the cryo holder can go. And we have double tilt holder that can help us align the crystal orientation, the zone axis, so that we can see atomic resolution on the sample. The third part is that it is stable enough. I mean, the drift is being controlled very well, so that when you have a STEM imaging, it's not like a TEM imaging, you have exposure time of 1 second or even short time. But STEM imaging takes, pixel by pixel scan, line by line scan. It takes a longer time. So if we see the image of atomic resolution, this means we have very good control in terms of drifting of the sample or the holder, and maintaining the structure of the sample. Jeff, please.
And it should be noted, Doug, also that the images shown here were acquired on a Joule ARM 200F, right?
Oh yeah, this is ARM 200F. I'm sorry.
No, that's okay. That's okay. Go ahead. Yep.
So this is another example we want to show to everybody that this holder works on a standard gold particle that was acquired. The image was acquired after 1 hour of insertion of the sample to the TEM. Then when this, so then the temperature was lowered to minus 170 degrees. So after 1 hour of sample introduction to the TEM, the temperature lowers to minus 170 degrees Celsius, and so we can easily acquire a TEM image with atomic resolution. This is another example to show the performance of the holder, that the drifting is being greatly mitigated over the sample. Please, Jeff. Yeah, this is a very interesting, this is a set of very interesting sample, a very interesting image coming from strontium titanate. This is atomic resolution of mapping. So we have different elements. So this is actually recording from EDS. From left to right, the left is the STEM image, then titanium, strontium, oxygen, and the lower three images are overlapping image. Overlapping image from SNT. So this is a STEM atomic mapping image, which is in my eyes very terrific, because if we want to acquire elemental map at atomic resolution with the high resolution TEM or high resolution STEM, we need to have 3 conditions controlled very, very well. First of all, drifting is minimum. Second part is that so because EDS acquisition takes longer time, so if we have uncontrolled drift or drift is out of spec, so you will see a very skewed image from the starting point of scanning and the ending point of the frame. But this image shows us very regularly patterned atoms from strontium titanate, and we can show each single elements on the image from this EDS acquisition. I think this is another proof of this of the performance of this holder, plus the performance of the ARM 200 TEM. Jeff, please. How we achieve this? I think there are a couple of key technical advantages we have seen on this holder. The first one part is the clapping of the sample. If we load the sample into this the chip of the TEM holder, so we have to lock the sample, TEM sample, into the chip in a very secure way, and reduce the possible vibration or drifting from this locking part. So this illustration here, the picture shows how the samples being loaded onto the tip, the holder, and locked into the sample spot. I mean the holder itself. So I myself particularly like this design because it's fairly easy to operate. So if you think about you are loading a specimen from outside of the glove box. So you have your two hands going through the very rubber gloves and try to operate everything from outside and see inside. It's not going to be easy. I mean, but this mechanism actually designed in a way that you don't have to really to go through those very clumsy steps to get the sample in. So the mechanism is very simple. You load the sample, put the sample in, you tap it a little bit, then put the clamp in there, then you tighten it, so it will get in there. I studied this design, for some time. In the past few days, I found this is quite interesting design here. Jeff, please. So this is now I think we have a few key technologies or key advantages in this cryo holder system that help us to be able to achieve the high resolution atomic imaging on TEM or especially STEM at the cryo conditions. The first one would be mechanical drift cancellation mechanism. So this is a patented technology from MEL-BUILD team. The second part is very high precision temperature control. So the range is plus minus 0.005 degrees Celsius. Most of the cryo control, temperature control for cryo system in the market goes to the second digits. I would say that's plus minus 0.01, 02 degrees Celsius. This goes to the third digit. That means that's a lot more stable than most of the cryo systems in the market. That I've been using this kind of technology for a while since I worked for helium-ion microscope system. So that requires cryogenic control for the source part. So this is a very good controlling system of temperature. And the third one, I would say I like the goniometer cover. I knew that the ARM200 has a goniometer cover for high resolution, long time STEM acquisition, STEM imaging acquisition. This is really isolating the goniometer and the sample rod sample from the environment of the laboratory. Most of the lab, you have airflow, uneven airflow, temperature fluctuation, and sometimes acoustic when people speaks and when people walks, and when some computer fan starts and stops, or something like that happens. So this is cover, which is really isolate the rod, the sample, the goniometer from the environment in your laboratory. This is another big contributing part from of the system that help maintain or achieving the results. So in short, we should say good temperature control and the mechanical drift cancellation mechanism plus the goniometer cover, that all together works very well to help us achieve atomic resolution imaging at cryogenic conditions for material science research. So Jeff, can you go to the next slide? So this is example we call it LLZ crystal atomic resolution STEM imaging. So if you look at the lower right corner, so we have a room temperature imaging, which is that image was acquired at 25 degrees Celsius room temperature. Because of the room temperature imaging. So we can see that the sample being when exposed to electron beam, so radiation damage happened already. So if you see the inside of the image of this room temperature 25 degrees C image, so that's the FFT pattern from that image. The sample actually is already damaged before before you record the image here. But after we lowers the sample to minus 160 degrees Celsius, so we can, from the left image, we can see all the patterns, all the structures are maintained. So if we have a small box showing up here, and we can clearly see those atomic structures being maintained very well, very well. This is a very good example showing, for material science research, for some beam sensitive materials, so excessive dosage that really damages the sample, the structure. So even if you get an image, so it will not be the authentic, will not reflect the authentic structure of your sample, because once you expose your sample to the electron beam, they already changed. So cryocooling to some degree, or to some minus 160, 120, or 170 degree is a necessity we have to have. It's a, it's a condition we have to have in order to see the true structure of your sample. Jeff, can you go to the next slide? Okay, so there are two type of holder configuration here. So some holders with can go to high resolution pole piece. Some can go to other kind of configuration of TEM. So they have different ranges of X to Y tilt, alpha, beta tilt. So this is a very flexible design. So depending on which kind of the TEM you have. Are they having a high resolution, very short pole piece gap, or you have analytical or tomography for pole piece gap for tomography or for high tilt? So you can have two kind of two choices of TEM holder. Jeff, can you go next? So I want to specially mention about this this small little tool here. So if we work in air, so if we have we don't need a glove box. We try to load the sample from a small desktop. So I don't think we really need this kind of tool or workstation stand, because I mean you are directly seeing everything from just in front of your eyes, and your hand can grab every tool to manipulate it. The thing is that for this vacuum transfer, everything is sitting inside of glove box. If you guys already working with the glove box before, you know how clumsy it would be. So if you have a like TM hold there, you have a TM grid somewhere, so in the vicinity, close the holder, and you need to use those gloves, work through the gloves to use a trailer to grab your sample and put it in onto the tip of the TM rod. It's very hard. It's very hard. So it's sometimes so you could push the holder to flip it, or you could drop the TM sample to somewhere. So with this stand here, it's really designed to help users to make an easy job in terms of loading TM samples onto the holder and secure the sample onto the tip with the specially designed clipping mechanism I just introduced a moment ago. But so without using it, it's very hard for user to to have a direct experience to see how useful this mechanism or this stand or this little tool is. But I can tell you, this is a very good, very well designed, just for making life easier for the microscopist by using the glove box. Jeff, can you go next slide? Yeah, we have a small video clip here showing after you loading your sample onto the clamping mechanism of the TEM rod. Now, how the samples or the tip is retracted into the rod. So, because we either use argon gas or nitrogen gas in the glove box, the samples are protected when retracting into the rod. So this means the samples always surrounded with the gas in glove box, either argon or nitrogen. So when you take this rod out of the glove box and move it onto the TEM, insert it into your goniometer, so the samples are still surrounded and protected by either argon gas or nitrogen gas. This is a very, very important part. I mean, even if you are a very skilled TEM operator, so if you don't have a gas protection from either argon or nitrogen from the glove box, just the 3 seconds you get it out of the glove box and put it into the goniometer of TEM, start pumping, the sample is already gone most of the time because it's exposed to air. Its samples are very thin, 20, 30, 50, 100 nanometer maximum. So with a few seconds of oxygen or moisture exposure, your sample is already destroyed. I mean, this mechanism design help us to keep your sample pristine from the glove box all the way to TEM goniometers. When you start pumping, get it into high vacuum level. So this is a very important part of this holder system. Jeff, can you move to next? Oh, this is an example. So that a Korean team, published their work at the Nano letter. This is how actually. So if you are interested in this paper, I guess so you can just go download it to see the details. How the workflow they used to use this holder to get a high resolution image with this cryo holder. I'm not going to go details on this because I think this is recorded. I mean, this paper you can just download from the supplemental information. All the details are already organized in there. Jeff, please.
Yeah, and just for the audience's information, if you'd like a copy of this this paper, this white paper, then just reach out to us and we'll send it to you. Okay.
Okay. So after that, a few slides of instruction of examples and the details of this holder system, I want to summarize, what we believe is the major advantage of this holder, that what contributes to the capability that we can use it to acquire high resolution atomic scale images or EDS mapping with this holder for those beam sensitive samples. The first one is, as I mentioned before, it's a patented technology. It's a mechanical drift cancellation mechanism. Second part is very high precision temperature control. That it's like 1 order of magnitude better than any holder that exists in the market. The third part is that the goniometer cover. I really like. This is this goniometer cover design. What really means a lot for material research is that a double tilting holder. So this helps us to align the crystal orientation so that we can see, or we can record the EDS spectrum on the atomic columns of the crystal. So without a double tilt holder, it's nearly impossible for material research to see the atomic structure of any sample. You would have to really go by chance. If you happen to move to a crystal that happen to be, I mean, its orientation happen to be on the wrong axis, you luck. I mean, you can get something. So without double tilting holder, most of cases like that. No, we have that capability. Jeff, please.
Mm-hmm.
Okay, so the previous slides, we basically introduced some results coming from the JUL ARM200F system. So the next some slides will show the data, the results we acquired from FEI thermal Fisher Talos microscope. So,
and I think we can skip this slide, right, Doug?
I think so.
Or, yeah.
I think so.
Okay. This is yes. So you can review these sources because this is from the Titan Cube. Okay.
Yeah, this is a summary slide that shows that the performance of the holder on the Titans. So at minus 170 or 160, minus 160 something degree, the holder performs quite well in terms of showing atomic resolution for gold particles and some perovskite samples and you know, so this is and the strontium titanate as well. Strontium titanate is a sample that most of STEM people uses to qualify or to see the performance of high-res TEM or high-res STEM, especially because it's easier for people to acquire either EDS map or EOS map, atomic column elemental information there. So this slide really shows us that so the performance of the holder and at minus 170 degrees Celsius, you know how the drift control part performs. I think Jeff, we can move to next slide then.
Mm-hmm. Yeah.
Yeah. So this is a strontium titanate sample, STEM imaging at high res at minus 160 degrees Celsius. So the small video in the middle shows that this is video recorded by iPhone, shows you know a bit of drift. So this is live imaging of the sample. Basically, we see the samples moving a little bit. This is normal, even without cryo, you know, holder in room temperature holder, high res holder. This happens as well at that higher magnification. But with the drift corrected the imaging, we can get very high quality imaging like the last one after filtering and stacking of the many frames onto each other to see the noise reduction after noise reduction method. So we can see the atomic resolution image for showing the different elements. So that's I think that's oxygen. So let's see, STO elements raw data. Hiroya, it's I mean the last one. That's I mean that's stacking of oxygen. Oh, sorry, that's strontium and titanium. Okay, it's this label there. there's label there. So I mean, this is a good example that to show how stable that holder is at minus 160 degrees Celsius for STEM imaging. So you scan your beam over area, and you can see from the video that it's so everything's moving, but it's within a spec that we can use drift correction to align those frames to eventually to get a high-res image atomic resolution EDS map on the right-hand side of the picture. Jeff, can you go to the next one? Okay, so this is EDS maps, EDS analysis of a still sample. I think, I'm not very clear about so why we would need a cryo holder for this map, but I would say this is showing that this holder, so if you use this holder for a routine sample analysis, that does not require a cryo condition. It still can be useful as a normal holder for either imaging or EDS analysis. Jeff, next, please.
Mm-hmm.
Okay. So this is the resolution shot. So this was done on the Titan at the Kyushu University, Japan. So the inset picture shows atomic resolution of this gold on carbon sample. This is a standard test. People want to say, hey, how good the performance of my TEM or of my holder, especially here. We want to test the holder or holder being put into the Titan TEM, how good the performance is of holder. This shows the holder performance meets the high-res requirement. Jeff, next, please. Okay, so this is another example that's strontium titanate at the high-res TEM mode, TEM imaging mode. This is not a STEM. I think this is a bit easier to acquire for strontium titanate at TEM mode, so exposure time is very short. But this was done at minus 162 degrees Celsius. So normally, cryo holder averagely drift, largely more largely than routine room temperature holders, high-res holders. But here, so after cool the sample down to 100 minus 162 degrees Celsius, we can easily achieve high-res TEM imaging. This is another example on the Titan at the Kyushu University.
Actually, this was done on the Talos, right?
Sorry.
Talos.
So this is on the nanoport, the FEI nanoport in Japan. It was
actually in the FEI nanoport lab.
Yeah, I'm sorry.
That's okay.
I thought this was the same sample as the previous one.
No, that's okay. Yeah.
Now, this is an example I think is very significant, for most of us when we evaluate the performance of the sample, because this is a sample that it's really beam sensitive. Perovskite samples are very beam sensitive, and it is a high-res atomic resolution on STEM mode. STEM mode is not like TEM mode. TEM mode, so you can really control the dose that well. So STEM mode, if you don't have enough dose there, you don't have enough signal there, right? So you have to apply enough dose there so that you get enough signal to get a good, relatively okay signal to noise ratio on your image. Otherwise, you don't see much. So this is testing the cooling part. So if we are not into the region of temperature that can maintain the sample, when beam comes, maintain sample pristine structure of the sample. So the sample will change. But if the stage is drifting, not within the spec we can control, that so you don't have a good stem stacking image, or so this is a high res part. So it's drifting is more it's more pronounced in terms of recording atomic resolution stem imaging compared to routine stem imaging here. So this exact tells us the high resolution part, high resolution performance on stem, extended time of acquisition, and temperature controlling, and the double tilting to help us align the zone axis of the sample or the crystal orientation of the sample. Altogether work well. We can make such an image here. Jeff, can you go next? Okay, so I mean the slide and the slides, I mean the next few slides shows the MEL-BUILD team is still working with FEI, not FEI, Thermo Fisher team in Nanoport, Japan, in FEI Nanoport, Japan, to get this whole workflow improved. Jeff, can you go? Yeah, this is also a drift corrected TM imaging. So with in TM acquisition mode, which samples is this? I don't see that sample. Okay, so this here, the period stage was used to for drift correction imaging. I mean TM imaging. So this 136 frames being acquired. This is without period staging activated, so we can see the atomic resolution on the sample. Jeff, next please. STEM imaging performance with the holder of 30 frames averaging. This is another TEM sample, a TEM acquisition. I think I'm not sure which sample is this. Without period stage activated. So basically, we can see how good or how stable the sample hold is. Move to next one. Eds spot analysis on the sample. It's supposed to be just on the copper grid. Jeff, next one. EDS mapping on this holder. Jeff, can you move? Okay, this is I think we introduced this slide before on the other slide deck.
That's correct. Yeah, and yeah. I think we've gone over this too, correct?
Yes,
so we don't need to do that. And we've talked about this, so I think, yeah. So that's it, actually. So that is the end of the presentation for us. And at this point, we're open to any questions from the audience that you may have.